Hello, everyone, and welcome to lecture 28 of computer architecture. Today, we're going to start talking about memory and cache. So last time, we ended the part on processor organization. We finished talking about we're in part 3 of microarchitecture, and we finished talking about how the processor is organized. And in the remaining part of the class, we're going to talk about how memory is organized. So in the first subpart of part 3, we looked at the data path. We saw how to build a data path that executes instructions, the instructions that we talked about in part 2 of the course. And we saw how to pipeline this data path to improve its performance so that we can begin executing the next instruction before the previous instruction has completed. And we saw how this improves performance. But we also saw how pipelining results in a whole bunch of hazards that we need to be able to deal with, how to enhance our pipeline, a forwarding unit that forwards data to deal with data hazard, and also a hazard detection unit that stalls the pipeline in case we have a hazard that we cannot avoid by forwarding. So this was kind of what we covered last time in process organization. There's a lot more that we can cover with process organization. What we saw so far in this course, because we have such limited time, are the very basics of designing processors. But there are so many more optimizations that go into designing processors that are available in your processors today. And these kinds of optimizations will take an entire course just dedicated to them. But we will not be covering them in this course. We've kind of covered the basic elements of building a data path and pipelining it. So what we're gonna move on to cover now is this block over here, this data memory block over here. So this data memory block that takes an address and reads or writes data to that address. What we're going to talk about in the remaining part of the course is how this memory is organized. Okay. Today we're going to talk about memory and cache. This corresponds to chapter 5 in the text. So let's get started. So before talking about memory, I'd like to talk about memory technology. So before talking about how it's organized, I'd like to talk about the different technologies that we use to build memories. And we spoke about this earlier in the semester. We spoke about SRAM and DRAM. And we said that SRAM is fast, but it's very expensive. DRAM is slower than SRAM, but it's less expensive. Okay, so here the latency I'm reporting is in nanoseconds. And the cost I'm reporting is the dollars that it takes for 1 gigabyte. Okay. A flash disk is even slower, much slower than DRAM, but it's less expensive. And magnetic disk is even slower than flash, but again, it's less expensive. So we see that there's this trade-off in memory technologies. Okay, and each of these memory technologies is based on a different kind of material and a different low-level devices technology. And we don't cover these technologies in this course. But the important thing to take away here is that there's a trade-off between latency and cost. The lower latency something is, the faster a memory technology is, the higher the cost of this memory technology. So when we build memories, our ideal memory would be a memory that has the latency of SRAM. So we would like to be able to access memory quickly, right? In the pipeline that we saw before, we were assuming that we can access memory in 1 cycle, right? So 1 cycle is of the order of a fraction of nanosecond. In the ideal memory, we want the latency of accessing SRAM. But we don't want our memory to be very expensive. We want it to have a huge capacity at low cost. So we would like to have the capacity and cost per gigabyte of disk. And the question is, how can we build a memory system? How can we build a memory system that gives us both of these, or basically gives us the illusion of both of them? A memory system where we can enjoy the high access latency of SRAM, but at the same time enjoy the high capacity and low cost of this. And the way to do that is using a memory hierarchy. So to arrange memory in a hierarchy. So rather than choosing one of these technologies to build our memory system, what we're going to do is we're going to combine multiple of these technologies. And the way we're going to combine them is in a hierarchy. And this hierarchy is going to be as follows. What we're going to do is we're going to use the smaller and faster. We're going to use the faster memory technologies. We're going to have a small amount of it. And we're going to use that for the data that is currently being accessed. And then we are going to use the slower memory technology that's cheaper, and we're going to have a larger amount of it. And we're going to use that for the data that is not currently being accessed. So we're going to have a very small SRAM in our memory system. We're going to have a larger DRAM, and we're going to have an even larger flash or disk in our system. And we're going to arrange these different these different components of the memory system in a hierarchy, so that we put the data that we are most frequently accessing in SRAM, the fastest technology, and the data that we're not currently accessing, we're going to put it in the slower technology. Okay. So the memory hierarchy is going to look like this. We're going to arrange memory in a hierarchy. We're going to store all the data on a flash or a magnetic disk. So all the data that's in our system needs to be put somewhere, and that's going to go in flash or magnetic disk. And among this data that's in flash or magnetic disk, the data that we are using frequently, we're going to store copies of it in DRAM, and DRAM is going to be smaller than disk because it's more expensive. Okay, so we're going to put the recently accessed data, we're going to put copies of it in DRAM, and this is called main memory. And then among the data that is in DRAM, among the data that is in the main memory, the data that are even more recently accessed, the data that has been even more recently accessed, we're going to put that in a component that's even smaller than DRAM. It's going to be made of SRAM. Okay, and we're going to call this the cache memory. And this cache memory is going to be closest to the CPU. Okay, and notice here I said recently accessed, or I said and nearby, right? So we're going to put the data that we recently accessed close by in the faster memories, and we're also going to put data nearby to that data in the smaller memory. And the reason we do this, the reason we said that we want to put the data that we are currently accessing close by in the fast memory. But here what we're saying is that we want to put the data that we recently accessed and the data that is nearby the data that we recently accessed in the small memories. And the reason is that recently and nearby are good predictors of currently. And what I mean by that is that the data that we currently want to access is most likely going to be data that we recently accessed or data that is nearby data that we recently accessed. Okay, and this is based on the principle of locality. Okay, so what governs the way we design memory hierarchies is the principle of locality. So what does the principle of locality say? The principle of locality is basically the observation that when programs access data, they usually access a small portion of their data in the address space at a time. So at any point in time, a program is not accessing all of its data. It's only accessing a small portion of that data. And this small portion of the data follows the following observations. This data has the access to the data has temporal locality. And what we mean by temporal locality is that items that are accessed recently are likely to be accessed again soon. And that's where the word temporal comes from, locality across time. So if I access some kind of data, I'm most likely going to access that data again. Now, where does this observation come from? You know, why do programs behave this way? Well, the reason is that we have a lot of these variables inside of our procedures, and a lot of times these variables are stored in memory, and we access these over and over again. So that's where this idea of temporal locality comes from: accessing something and accessing it again. Also, we shouldn't forget that we don't just have data in memory; we also have instructions in memory. And if I have a loop, for example, I'm looping over the same instructions over and over again, right? So I'm going to load the same instruction multiple times from the instruction memory. Okay, and that is where this idea of temporal locality comes from. The other type of locality is spatial locality. And what spatial locality says is that items that are nearby the items that we recently accessed are also likely to be accessed soon. So in other words, this is locality across space. Temporal locality says, there's locality across time. It says if I access something, I'm likely to access it again, the same thing again. And spatial locality says that if I access something, I'm likely to access things that are close to it later on. And where does this idea of spatial locality come from? Where does this idea that programs, when they access data, they're probably going to access data that's close to it? Well, it comes from things like arrays, for example. So when I'm accessing an array, let's say a lot of times we go through an array sequentially, right? We go from the beginning of the array to the end of the array. So in this case, when I access an element in the array, there's a high chance that I'm going to access the next element after that. Okay, and then there's also for instructions, like we said, instructions are also in memory. So when I access an instruction from memory, I'm most likely, there's a high probability that I'm going to access the next instruction because that's how programs execute, right? Unless I have branches or jumps, programs go through instructions one instruction at a time. Okay. So this is why we have this idea of we're going to leverage this principle of locality, temporal locality, and spatial locality in order for us to build our caches and optimize our memory stuff. Okay. So any questions so far? Is this clear to everyone? Okay. So having spoken about this principle of locality, let's see how we can organize our memory into a hierarchy. So in a memory hierarchy, we have multiple levels. Okay, and here I'm going to show just two levels. There are multiple levels in the hierarchy, not just two, but this two is just for an example. So we have a processor, and the processor can access a small and fast memory, and then this memory is going to contain copies of data that are in a lower or in a higher level. We consider this to be a higher level. So we have a higher level of the memory that is larger but slower. Okay, and what happens is when the processor accesses data, what we do is we bring the data from the higher level of the memory. We copy it to the lower level of the memory. That way, if the processor wants to access it again, it finds it in this lower level of memory, in this small and fast memory, and can access it at a fast with low latency. Okay. So given this kind of organization of memory, there are a few terminologies that I would like to introduce. The first is the idea of a block or a line. So a block or a line is the unit of copying data across the memory hierarchy. So for example, when I access data and I don't find it in this level, I find it in this level, and I want to copy it from this level to this level, right? I copy a certain number of bytes. Okay, I don't just copy one byte, right? I'm going to copy multiple bytes. And the number of bytes that I copy, this is called a block or a line, right? We often say a cache block or a cache line. Okay, and this is the unit of copying data across the memory hierarchy. And this may be multiple words, right? So when a processor usually it loads a byte or it loads a word, right? Instead of copying just one word or one byte from the lower level to the higher level, we usually copy multiple words. And this is based on this idea of spatial locality, because if we access a word, we're most likely going to access the word that's next to it. So we might as well copy multiple words. And we'll see this later. But for now, I just want you to be aware that a block might be multiple words. We say that a hit occurs when the access data is present in the level that we care about. So for example, if the processor tries to access data and it finds it in this level of the hierarchy, then we say that if we have a cache over here, then we say we have a cache hit. Okay, because it found it. If it doesn't find it over here, that means we don't have a hit. We have something called a miss, and we'll talk about a miss. So the hit ratio is the percentage of hits per access key. So for example, if half the time I find my data in this level of the hierarchy, and the other half I don't find it, and I have to go to the higher level of in memory. Then we call this then we have a hit ratio of 50%, right? Because half the time, half our accesses are hits, and the other half are not. A miss occurs if the access data is not present. So if the data is present in this higher level in the hierarchy, but not present in the lower level, then we say that we have a miss because the processor tries to access the data, it doesn't find it. So it has a cache miss, it has to go to the next level in the hierarchy. Okay. So here in the slides, I'm using upper level to refer to the level that's closer to the cache, and lower level to refer to the level that's farther away from the cache. But sometimes people will use the opposite terminology. So sometimes people will refer to the level that's close as the lowest level, and the level that's farther away as the higher level. Okay, and these terminologies can be sometimes confusing. Usually, kind of when we talk about things, we'll refer specifically to the name of the level, and we'll introduce the name of the level later on. Okay. All right. So a hit is when we find the data that we want in the level that we're interested in. A miss is when we don't find the data that we want in the level that we're interested in, and we want to go to the next level and copy that data from the next level. Okay. And by the way, we could have multiple levels over here. So I could come to the next level and also not find the data here and go to the level that's below this one. So here I would have a miss at this level and another miss at this level. Okay. The miss penalty is the time that it takes to fetch data from the lower level. Okay, so when I try to access this level over here that's nearby the processor and I don't find the data, right? This next level here is much slower than the level the level that's close to the process. So because this is much slower, we're going to need more time to access the data in this next level, and the time that we need to fetch the data from this next level is called the miss penalty. Okay. The miss ratio is the percentage of accessees that miss, right? And obviously, since we already have a hit ratio, so what is the relationship between the miss ratio and the hit ratio? So the hit-miss ratio is going to be 1 minus the hit ratio, right? Because if 97% of my accessees hit, then 3% of them miss, okay? If 80% of my accessees hit, then 20% of them miss, okay? And then finally, when we miss, the access data is stored and supplied from the upper level. So here, when the processor tries to access this level here and it misses, what we do is we go to the next level, we get the data, we bring it to this level over here, and then the processor accesses it from this level. Okay? Any questions? I see several questions. So someone's asking, how large can a cache block be? It depends on the architecture, or more precisely, it depends on the microarchitecture. Different caches could be designed with different block sizes. And in fact, next lecture, we will talk about the trade-offs that come in when determining what the block size should be. Okay? Typical block sizes are things like 128 bytes and around that range. So someone's asking, a hit is when the data is already available in the upper level. Yeah, so a hit in a level is when a data is present in that level. And if the data is not present in that level, then we have a miss at that level. So for example, if the data is present here, but not present over here, then we say that we have a miss over here, and then we have a hit over here. Okay? Okay. So someone's asking if the hit ratio is low enough, caching is less significant. Yes, of course. You know, caching is only meaningful when you have locality, right? So if you have locality, temporal locality, and spatial locality, which most programs do, then caching is very useful. But if for some reason your program has very bad locality, then caching becomes less and less useful, because this idea of caching relies on that when you access data, you're going to access it again. So it makes sense to put it somewhere that is closer. So someone's asking if the block is loaded at the same time. I don't think I understand the question. So when the processor accesses data and doesn't find it here, it tells this level in the hierarchy will tell the next level in the hierarchy to provide it with the data. And we will look at the hardware that does this later on in today's lecture. Okay. All right. So this covers memory hierarchy level. So now let's talk about block placement. Let's talk about how we place blocks in these levels. Let's assume that I have this memory, and memory is very large. We usually have 32-bit addresses, and these 32-bit addresses allow us to address 4 gigabytes of memory. And of course, there's also 64-bit systems that allow us to address even more memory. But for simplicity, let's assume we have this memory. This memory has 5-bit addresses, and consequently, it has 2 to the power 5 different memory locations that we can access. Okay, so it has 2 to the power 5 or 32 blocks. And let's assume that we have a cache for this memory, right? This memory is slow, so we want to create a faster and smaller cache for it. And let's assume that this cache has 8 blocks, and obviously, since we have 8 blocks, we need 3 bits to index the cache. So the question is, how can we, if I'm accessing a block from this memory, and I want to bring this block into the cache, where do I place this block in this inside this cache? Where can I place it? Do I place it anywhere? Is there a specific place to place it? This question has to do with block placement. So there's actually different types of cache designs. Some caches let you place it anywhere. Some caches only let you place it in specific locations. And the first design we're going to talk about today is the direct map cache. And a direct map cache is a design where is a design that maps every block in memory to one specific block in the cache. So each one of these blocks in the memory can only map to one block inside of this cache, right? So if I copy a block from memory to the cache, there's only one place I can ever put it. And in this example over here, I have this block at address 11010. I can only put this block in a direct map cache. I can only put this block in one of these blocks, which is block 010. And how do I determine that? I'm going to look at a specific set of bits inside of these this address, specifically the lower 3 bits, and we're going to use the lower 3 bits in the 5-bit address to index the cache. Okay, so what we will do is we'll take these 5 bits, we're going to look at the lower 3 bits, which are 010, and we're going to use those to decide where we're going to take this block and put it in inside of the cache memory. Okay, so for example, the cache, the block 00000 is going to map to the cache block 000. The block 00001 is going to map to the cache block 001. Next one to the next one, next one to the next one, and then when we get to 00111, that's going to map to 111. But then when we come back here, when we get to 01000, that's going to go back and map to the location 000. Okay, now there's a problem here when we do this. What's the problem? And now the problem is now we have multiple locations in memory that are going to map to the same location in the cache. Now this is normal, right? I'm trying to use a smaller data structure to keep around data from or not data structure. I'm trying to use a smaller capacity structure to keep around data from a structure with larger capacity. So it's normal that I'm going to need to be able to use the same block to put different blocks from the larger memory at different times. And we're only going to be able to have one of these at any point in time. Okay, so I can't have both 00010 and 11010 in the cache at the same time, I'm able to have one of them at the same time. Okay? Only one of these will be able to be in the cache because they all map to the same block, and only one of them is going to be able to use that block at any point in time. So since we have this situation, since we can only put one of them at the same time, the question is, if when I come to access my cache, so if the processor is coming to access this cache, and it comes to access the cache line or the cache block at index 010, how is the processor going to know if this cache block at 010 refers to the memory block at 00010, or the memory block at 01010, or the memory block at 10010, or the memory block at 11010? We need a way to differentiate between these. We need a way to figure out which of these blocks in memory the block in the cache refers to at a given point in time. So how can we do this?
We store the higher bits of the address in the memory in some bits associated to the block in
Right,
the
exactly.
cache.
Right, exactly. So here we'll notice that all these bits, all these blocks in the big memory, what they have in common is these lower 3 bits, 010, 010. They all end in 010. That's why they all map to the same cache block. What differentiates them is the remaining 2 bits. Here's 00, 01. This one is 10, and this one is 11. So what we can do is when we bring this data into the cache, what we can do is we can also store in the cache these remaining 2 bits to be able to identify which of these blocks in the memory the data that we have in the cache refers to. And we call these 2 bits these 2 additional bits that we store in the cache the tag. Okay? Now it could be the case that this cache line, this block, is empty. It could be the case that none of these 4 blocks are sitting inside of this cache block at a specific point in time. So we don't only need to store the tag, we also need to store some kind of we also need some kind of way to identify whether this cache line is empty or not. And for that, we're also going to have something called a valid bit. Okay, so to summarize, how do we know which memory block is stored in a cache location? The way we know is that we're going to store the address of the block along with the data. And we don't need the entire address because the index is implicit. So we're only going to store the higher bits. And these higher bits are going to be called the tag. Okay? And the other question was, what if there is no data in a location? How do we identify if there is data or there's no data? We're also going to have a valid bit, and the valid bit is going to be set to 1 if data is present, and it's going to be set to 0 if data is not present. And initially, when our program begins, the valid bit is initially going to be 0 because initially we're not going to have any data in the cache. Okay, not specifically when our program begins. You'll find out later on that that's not exactly the case. But in general, right, at the kind of the beginning of time, when things begin in our computer, the caches are initially going to be empty and my valid bits are going to be 0. And if for some reason I had to remove a cache line from the cache, then the valid bit will also return to 0. Okay, so having said all of this, let's do an example. Let's say we have a direct map cache with 8 blocks like the one we had before. This direct map cache is going to have the data that we have, the data that we got from the memory, and it's also going to have a tag for that data, and it's going to have a valid bit. And initially, all my valid bits are going to be 0. Here it says n for no, so here n means 0. So when my valid bit is set to 0, that means there's no data in the cache. That's what this n over here means. Okay. Now what the processor does is it tries to access make an access at address 10110. Okay. So first of all, which cache block is this access going to map to? Right, we're going to look at the lower 3 bits, and it's going to map to access 110. So what we do is we're going to take this address, we're going to extract these 110. We're going to come down here, we're going to look at the block 110, and what do we find? Do we find our data here? No, we don't find the data. We find that this cache line is invalid. Cache block is invalid. So what do we do in this case? Well, do we hit or do we miss? We have a miss, exactly. So in this case, we're going to have a miss, right? Our cache block is 110, and we're going to have a miss. So we're going to go to the next level in the memory hierarchy, and we're going to fetch that data, and we're going to bring it now. We're going to put it in our cache, okay? We're going to save the tag. Where did I get 10 from? Why is the tag 10? Right, I get it from here. These remaining 2 bits, the leftmost 2 bits, these are the tag. And I'm going to set my valid bit to 1. Okay, so here yes means that this cache line is valid. Okay, so I'm going to set my valid bit to 1. Okay, now I have another memory access comes along, right? 11010. What's going to be the index here? Okay, 010, right? So do I have a hit or a miss? Right, I have a miss, right? So my cache block is 010, I have a miss. So I'm going to bring the data from the address 11010 and put it here. And I'm going to set the valid bit to 1. And I'm also going to store the tag. And where did this tag come from? Where did the 11 come from? Came from these remaining 2 bits here, 11. Okay. So now another access comes along, 10110. Okay. So what's the index here? 110. So I come here to 110. Do I have a hit or a miss? Right, so first of all, the cache line is valid, so that's important. But the other important thing to check is whether I have the same tag, right? Because this tag might be 11, or it could be 01. So I need to make sure that I have the same tag. And in this case, I do have the same tag. I have a 10 here and a 10 here. And based on that, I conclude that we have a hit. Okay, now another access comes along, 11010. Where does this map to? Which index? Right, 010. Are the tags the same? Right, it's valid. First of all, is it valid? Yes, it's valid. Are the tags the same? Yes, the tags are the same. And therefore, I have a hit. Okay, now another access comes along. What's my index here? Right, 000. What's my tag? 10 is my tag, right? Do I have, so 00 is here. Do I have, this line is invalid, so obviously I have a miss. Right, so I'm going to get the data. Okay, I'm going to put my tag in over here. Next comes along, next I have 00011. Okay, what's my index here? 011. I come down to 011. It's not valid, so I have a miss, right? And when I have a miss, I'm gonna get the data here. I'm gonna put my tag. What's my tag? Right, 00, exactly. Okay. Then I'm gonna have another address come along, 10000. What's my index? Right, my index is 000. Do I have a hit or a miss? Right, I have a hit. They have the same tag, so I have a hit. Okay, so I have this is my index is 000, my cache block, and I have a hit. And now I have the next access comes along. I have 10010. What's my index here? What's my cache block? 010. Do I have a hit or a miss? Right, I have a miss. Why do I have a miss? Right, exactly. So this cache line here is valid. However, the tags are not the same. Okay, so when I compare the tags 10 and 11, I figure out that the tags are not the same. And because the tags are not the same, what do I need to do? I have a miss. And because I have data sitting here, I need to go and fetch 10010 and put it in my cache, but I have this data sitting here in my cache. So what do I have to do with this? I'm going to need to remove this from my cache, right? I'm going to need to remove this from my cache. Yeah. So I'm going to have to evict this old block from my cache, right? Now, if the value of this block did not change, I don't have a problem. If it changed, I may need to do something else, and we'll talk about that later. But the point is that we need to evict the old value from the cache and replace it with the new value and update the tag. Okay? So that's kind of an example of how caches work. Any questions about caches? Everything's clear? Okay, great. All right, so having spoken about how the cache work, let's look at at a more realistic example of how we take our address and break it up in order for us to access the cache. Okay, so in the previous example, we gave a cache that had 8 blocks and 5-bit address, and we were using 5-bit addresses, and that was just a toy example to help explain the concept. In practice, we have caches that are much larger than that. So let's consider a cache that has 2 to the power 10 or 1024 blocks, like this one. And for every block, we have a valid bit, we have a tag, and we have the data that's stored in that block. And let's assume that our block is 1 word or 4 bytes. Okay. Later on, we'll look at cases where our block is larger than 4 bytes. But for today, let's assume that our block is 4 bytes. Okay. So every time we have a load word instruction, we give it an address. We're going to go and we're going to get all the data inside of a specific cache line. Okay. Now the question is, given a 32-bit address, so when I have load word, the processor is going to give me a 32-bit address, and it's going to tell me, hey, please go get me the data that's at this 32-bit address. So the question is, how do I use this 32-bit address to access my direct mapped cache that has 1024 entries? Well, what I need to do is I need to take this address and I need to subdivide it into parts that I will use to access my cache. Okay? Now, the first thing that we need to consider when we divide this address up is that if this is a load word instruction, right, our data here is a whole word, right? So the data over here is a whole word. And we know that words are stored at multiples of what? Multiples of 4, right? Multiples of 4. And what does that mean with regards to the address of a word in the cache? What do I know about the lower 2 bits? Right, the last 2 bits are always 0, exactly. So the lower 2 bits are not needed because the lower 2 bits are always 0. Okay, so the address of a word is always going to be is going to have 0 in these 2 bits. Now, if I have load byte instead of load word, then these lower 2 bits are no longer 0. They might be something else. But in that case, what I would do is I would load the word from the cache, and I would access the specific byte inside of that word. But it's not going to impact where this data is going to be in the cache, in which block. Okay, so what we're going to do is we're going to use these lower 2 bits these lower 2 bits. We're going to ignore them because we're accessing whole words right now. And then we're gonna use kind of some bits from these remaining 30 to figure out which index we're gonna map to. Now, how many bits do we need to? How many bits from this address do we need to figure out which index we're gonna map to? So we have 1024 different cache blocks. Okay, that's 1024 different indices. So how many bits do we need for 1024 different indices? We need 10 bits exactly. So what we will do is we have this 32-bit address, 2 of the bits we don't care about, and then from the 30 bits remaining, we're going to use 10 of these bits to determine which block we're going to map to. Okay, so we're going to extract the 10 bits. We're going to call these the index. So the next 10 bits are going to be the index. Those are bits 2 to 11. Okay, and we're going to look at these 10 bits, and we're going to use these bits to determine which cache block this address is supposed to map to. Okay. All right. Now that we have found the cache block that we care about, the next step is to do what? Oh, someone's asking why these bits in particular. So it turns out to be kind of good design to use these 10 bits to access the lower 10 bits to access the cache. It does not necessarily need to be the case. We could have used a different set of 10 bits. However, using the lower 10 bits will give you the pattern of when you access data that is next to each other, that this data ends up being in consecutive cache lines, and then you wrap around when you kind of exceed these 10 bits. Okay, so we're going to use bits 2 to 11 in order for us to get a 10-bit index that will help us identify where to which block in the cache this address refers to. So just like in the previous example, we had 5-bit addressees, and we used the lower 3 bits in those 5-bit addressees to determine which cache block we want to index. Here we have a 32-bit address, and we're going to use these 10 bits in our 32-bit address to identify which cache block we would like to index. Okay, is that clear to everyone? Okay, so I have an address. I ignore the lower 2 bits. These are always 0, 0, and these are and I don't care about those when I'm accessing a full word. Okay, I use the next 10 bits to index the cache to figure out which cache block is the one I'm interested in. Okay, so let's say I reach this cache block. Now what do I need to do? So what did we do before? When we indexed our cache? Well, the first thing we need to do before we check if the tag matches, we need to check if this cache line is valid or not. So what we're going to do is we're going to read this valid bit over here, and we're going to check if the valid bit is set or not to see if the cache block is empty. Now, if the cache block is not empty, then what do we do? Right, we're going to check the tag. So here we had these 2 bits we ignored because they're always 0, 0. We had these 10 bits were indexed. So how many tag bits do I have left? 20, exactly. So these remaining 20 bits, I'm going to take these 20 bits. These are going to be my tag. And I'm going to take these bits and I'm going to compare them to the tag that is stored in the cache. And if these 20 bits, after I compare them, I compare the tag in the address to the tag in the cache block. If they are equal, right? If the cache line is valid and the bits are equal, that means I have a what? I have a hit, exactly. So I'm gonna have a little AND gate over here. If my valid bit is set, and if my tag in the address is equal to the tag in the cache, that means I have a cache hit. And that means I tell my processor, hey, processor, I have a cache hit. And then once I have a cache hit, what do I need to do? Right? Do I just tell the processor I have a hit? I need to actually give it the data, right? So I found the data in the cache. So I read the data from the cache and I give it to the processor. I return the data to the processor so the processor can use it. Okay? So that data memory block that we saw in the pipeline, or in the data path, that's what that data memory block was doing. It was taking the address that we were giving it, breaking it up, indexing the cache, checking the valid bit, comparing the tag, and if we have a hit, accessing the data. Now we could have a hit, but we could also have a what? We could have a miss. So if we have a miss, what do we need to do? We need to go to the next level in the cache. Okay, we need to go to the next level in the cache. So on a cache hit, the processor just proceeds normally, right? So everything that we showed you on the slide, right? We can do all of this in one cycle, right? In the pipeline data path that we showed you before, okay? So if we have a cache hit, then the memory stage takes one cycle and the processor proceeds normally. It's like we don't feel anything. But if we have a cache miss, that means we need to go to the next level in the memory to fetch the data, and that is going to take time. Okay, so in this case, what we're going to have to do is we're going to have to stall the pipeline, and we're just going to have to sit there and wait and wait and wait until the data arrives, and we're going to fetch the block for the next level of the hierarchy, and we're going to resume the execution when the block arrives. And what does that mean? What does it mean to stall the pipeline? We're not going to get into the details of how we're not going to go to the pipeline and modify it to show how we stall when we have a memory access. So you don't have to worry about that when we have a cache miss. But you just need to know that when we have a cache miss, we're going to have to stall the pipeline until it arrives. And which stages does that involve? Stalling the pipeline. Which stage do I stall in until the data arrives? Right, the memory stage or what? No, not the ID stage, the instruction fetch stage, exactly. So I have two different memory structures in my data path, right? If I have a data cache miss, I'm gonna have to stall in the memory stage, and when the data arrives, I'm gonna restart the memory stage. If I have an instruction cache miss, then I'm gonna have to stall in the instruction fetch stage, and I'm going to have to restart the instruction fetch stage when the data arrives. Okay? So this was kind of a brief overview about caches. We're going to continue our overview of caches next time. But if you want to read more about what we covered today, you can refer to sections 5.1, 5.2, and 5.3 in the textbook. Okay? Any final questions? All right, if not, then that is all for today, and I will see you next time. Bye, everyone.